Good. So wonderful. A very good morning or afternoon or evening, everyone, depending on the time zone you're in. It's my great pleasure to welcome a friend of the family, Hakop, who I got to know quite some years ago, actually at the University of Sydney, where he was doing a PhD with another friend of the family, with Steve Bartlett, and also a bit with Steve Lamia, working on notions of simulation in the strong and weak sense, and quite related to the work that we will hear about today. Later he moved to the PI in Canada, and today he will speak about a sophisticated topic that's close to our hearts. Maybe when he speaks about improved upper bounds on the stabilizer rank of magic states, that's related actually to the strong simulation of Clifford dominated quantum circuits in the first place. So thanks for coming. That's all we can offer in these awkward days, to have an electronic talk in the sense, but thanks for willing to give this talk. We are very much looking forward to what you have to say. Thanks a lot for coming, and the stage is all yours.
Excellent. Thank you very much, Jens, for having me here. It's always nice to talk and meet the people in your group. And thank you everyone for being interested in this talk. So I'm Hakop Pashayan. I'm from PI and IQC, and I want to talk to you about this paper, which you might have seen on the archive, and it's joint work with Hamam Qasim and David Gossett. Okay, so I want to kind of set up a little bit of background and talk about simulation, classical simulation, a bit more generally before diving into the very specific topic. So I want to just set up some notions of simulation, and in particular, I want to define these two quantities, PC and PQ, before I define notions of simulation. So let C be some description of a universal classical circuit. So ands, ors, and NOT gates. Then these define some Boolean function that maps bit strings to yes or no, 0 and 1. Then we can kind of define a probability PC that depends on this description of the classical circuit. And the probability is defined as follows. If you imagine generating a random uniform bit string and evaluating it according to this Boolean function, you want the probability of seeing the 0 outcome. So it's some probability that you could compute if you could just run the circuit many times. So an analogous quantity is defined here, PQ, and this takes in a description of a quantum circuit, a universal quantum circuit, which tells you, describes some unitary that maps your initial state to some final state. And this description also tells you how many qubits you measure. So you measure the first W qubits of this state, and this PQ is the probability that you see the all 0 outcome on the measured qubits. Okay, and that quantity is given by the squared 2 norm of this quantum state. Okay, so that defines two different probabilities. And then we can define a bunch of simulation tasks associated with decision problems or estimation problems associated with these probabilities. So I want to break these up into kind of 3 distinct categories. And really, we're going to be focused on these last 2, but I'm talking about these first 2 as a reference, because they may be more familiar. So this the first task, and each of these tasks is going to get harder, so they get harder as we go down. So the first task is, given this classical description, decide if this probability is less than 1/3 or more than 2/3. So you promise somehow that it's in one of these 2. And you need to do that in polynomial time. And this essentially defines the complexity class BPP, the class of problems that you could solve with a probabilistic Turing machine. And the next task is the quantum version of this. So here you're given a description of a universal quantum circuit. You know that you're only going to measure 1 qubit, And you have to decide if the vulnerable probability is less than a third or more than 2/3. And you have to do this efficiently. And so this essentially defines the class BQP. And these two are decision problems. And this third example is kind of a function problem version. So it's slightly different. Given the description of the quantum circuit, we can measure more than one qubit here, so we can measure as many qubits as we like. And what we want is an output of an estimate of the vulnerable probability. And this estimate has to be of a certain quality. So in particular, the amount of error in our estimate has to be less than epsilon for some epsilon. And we need the runtime to be a polynomial in the number of qubits and in inverse epsilon. And so I'm going to refer to this notion as additive error estimate of vulnerable probabilities. And the thing that's kind of important is that both of these notions of simulation, or both of these tasks, can be accomplished by a universal quantum computer. And this fourth task here is well beyond the ability of a universal quantum computer. And the task is as follows. Given a description of a quantum circuit, output an estimate of the vulnerable probability to what is called relative error. So now the amount of error you have has to be some fraction of the true vulnerable probability. And since this vulnerable probability can in general be exponentially small, it's actually a really strong requirement on the accuracy. So in general, a problem like this is sharp P hard, which means it's harder than this general very hard counting problems such as number SAT, where you have to count the number of satisfying formulas to satisfying assignments to a SAT formula. And so the focus of this is really going to be the focus of this talk, and the notion of stabilizer rank is really going to be closely associated with this notion of simulation here. So we expect that simulators that run in the runtime of the stabilizer rank are gonna achieve these complex tasks, right? So we expect them to be slower or take more computational resources, classical computational resources to run. But I'm gonna, so although this is gonna be the focus of this talk or the focus of this paper, a lot of my previous work has focused on particularly this notion of simulation here. And so I will kind of talk about the connections between these two and try to give a more general picture of notions of simulation or simulators before focusing on the results of this talk. So to start, I want to talk about this kind of maybe heuristic or way of thinking about simulation that I think is helpful or helps me at least categorize how to think about simulation. So I just want to kind of talk about it a little bit. So an approach to simulation or a way of thinking about simulators, although this doesn't apply to all simulation schemes, is the following. So one has to kind of choose a language in which to talk about a universal quantum process. And this might involve, say, choosing a gate set, and a language in which where you describe arbitrary quantum evolution. And then one might choose a classically simulable free subtheory within this language. So something that's actually easy to completely simulate using a classical computer. And then we might see a resource, some kind of resource appear that quantifies how far the thing we're trying to simulate is from this free subtheory that's easy to simulate classically. And in general, the classical simulation runtime will scale in this resource, which might be which we would expect to be exponentially large for difficult circuits that sit outside of this classically simulable space. So this is just a cartoon, but maybe it gives you a bit of an idea of how things work. So an example, these I'm going to give you two toy examples, and then I'll give an example that's really relevant to the task and the focus of this paper. So the first example is we describe universal quantum mechanics by starting in a computational basis state, and then using this gate set, which consists of the Toffoli, so control not, the C not, the X, and the Hadamard gate. This is a universal gate set, and then the free classical theory is basically reversible classical computation, since the Toffoli can be used to construct reversible and not gates. And then the resource becomes 2 to the number of Hadamard gates, because you could write a Hadamard gate as a linear combination of Z's and X's. And so you could take a circuit like this, which is constructed from this gate set. And you could kind of look at these Hadamards as either one or the other. So there's 2 to the number of Hadamard branches, and in each branch, you're choosing which term you're looking at in this Hadamard decomposition. And when you choose the term, then everything becomes easier to classically compute. So there's a deterministic evolution of the input bit string. And these Zs give you global phases at the end, but everything kind of becomes easy, and you see a kind of toy example of this picture. And there's kind of 2 very nice papers that talk about approaches that are similar to this. Another example I want to just briefly mention is where we describe universal quantum mechanics by starting in a computational basis, and then we can apply gates from single qubit or 2 qubit gates that are arbitrary, and we think of the free classically simulable circuits as the non-entangled circuits that have no 2 qubit gates. And there, the resources are various measures of connectivity. So an example is you look at a circuit like this, where these could be arbitrary single qubit gates, and these could be arbitrary 2 qubit gates. And then you essentially have a tensor network that you contract in some ordering, and the number of legs you encounter in your tensor gives you some measure of the connectivity, and it gives you some classical cost hurdle, and there's and you proceed using whatever algorithm you like. And there's kind of various more sophisticated algorithms for doing this, where various resources arise that measure the kind of distance in this way.
Can I ask you a question about this?
Sure.
In that, I mean, that's great, but of course, what matters here is the order in which you do the contraction, right? I mean, there will be, in one way or the other, the tree width of the graph coming into play. So we have a tree; it's very, it's contractible in poly time, but otherwise there will be exponentially scaling overheads. Are you like considering a certain order in which you contract, or are you optimizing over certain orders, or
well, I mean,
assign the certain cost?
In this example, I'm speaking very generally. Certainly the order matters, and a classical simulation algorithm should specify the order in which you do the contraction, and that order, in some sense, sets up a bound on your resource. And if if you're doing it in an optimal way for the computational resource you have at hand, then this upper bound might be tight. Okay. But it's kind of I'm being kind of agnostic about.
Okay, wonderful. Thanks.
Okay, so now I want to move on to an example that's going to be much more relevant for this talk. But I just want to maybe have that framework in mind. So in this example, we start in a computational basis state, but we add to this computational basis state a plentiful supply of magic states, these T states that are defined up here. And then beyond this, everything is Clifford. And here the free subtheory is the stabilizer circuits. And this resource is going to be some measure of the magic that's in this initial state. Okay, so this little bit here is just to convince you that this is in fact, a universal model. So if you haven't seen this T gadget, this is where I'm going to kind of describe this. So the Clifford circuits combined with T gates are universal for quantum computation. And there's this thing called the T gadget, courtesy of these papers, that will basically allow you to replace a T gate by this gadget. And this gadget adds an ancillary qubit initialized in the T state. You do a controlled NOT operation, then you measure, and conditioned on the measurement outcome, you apply a phase gate. So if the measurement outcome is 0, do nothing. If it's 1, apply a phase gate. And if you do that, then the input state gets a T gate applied to it. So it's exactly the same as a T gate. So if you take this gadget and replace every instance of a T gate here with one of these gadgets, then your circuit looks like this. And I've done a little trick here where I've post-selected on the measurement outcomes rather than doing classical conditioning and controlled phase. And there's some technicalities where there's some factors that are going to crop up if we do this, but none of this is going to be important when we're dealing with relative error. So in general, your universal quantum circuits can look something like this. And now, courtesy of an observation by Hector Garcia in his PhD thesis, one might consider taking these multiple copies of a T state and writing them as a linear combination of stabilizer states, these phi i's at stabilizer states. And if you do so, you might hope that you could somehow treat each term as a separate stabilizer input getting fed through a stabilizer circuit, a Clifford circuit, which is all classically simulable. And so you could somehow try to do universal quantum computation. And there you're going to have some resource cost that depends on the number of terms you had in your decomposition. And this K kind of pops up as your resource cost.
Can I ask another question? Maybe a possibly somewhat stupid question. I mean, that makes, of course, perfect sense. And also the accounting for resource makes perfect sense. But in principle, you could also think of convex combinations or even linear combinations of terms, right? You could have like superpositions and like linear combinations of quantum states, of density operators as well in your notion of strong simulation. You don't seem to consider this, right? But is this a possibility? Have you thought about this?
Density states? You're talking about density states?
No, the mixed states. I mean, just
yeah, absolutely. And actually, I'll talk about this a little bit later.
Okay, good. Because that would be another kind of knob to turn. And I mean, again, you can reasonably account for the resources that come in. And it's clearly, I mean, it's clear that this offers an advantage when you can have like linear combinations of exactly efficiently simulatable expressions. But anyway.
Excellent. I'm glad you asked that question because it justifies me talking about that in about 5 minutes.
Wonderful. Okay,
excellent.
Thanks.
May I ask perhaps a more naive question? So in regards to Jens's first question, I was just thinking about your setting right now. Does the fidelity of the magic state matter for you?
I think, again, this is going to be addressed in the next slide. But here we're talking about exact magic states. Yeah, and maybe I should clarify that I guess there's two different kind of ways where fidelity might matter. So one is in in the quantum description of the system you're trying to simulate, right? Like, because there's a true system you're trying to simulate, and then if you try to do a quantum implementation of it, you might find that your T-gate is not perfect. But then alternatively, in your classical, like you might have a perfect T-gate in your quantum implementation, but then your classical implementation is not simulating exactly a T-gate, but something close to a T-gate. So the first one I'm not going to care about, because I'm going to assume we're simulating a perfect quantum circuit. The second one we're going to discuss in the next slide. And so with this kind of idea, this notion of stabilizer rank is, formalized by Rabi-Smith-Smolin and then Rabi-Gossett, and it's defined as follows. So it's a quantity, it's an integer for any pure state that you input, and it's defined as the minimum k, such that this pure state can be written as a linear combination of at most k stabilizers. Okay, so with this, we can talk about stabilizer rank simulator. So the basic idea goes as follows. First, we decompose our magic states into these linear combination of stabilizers, and then we pick one term at a time, and we construct this stabilizer state, and then propagate it through the circuit, propagate it through the measurement or the post-selected projection, and what we're left with is a state on this on the register here, the stuff that hasn't been post-selected, and we want to compute the squared 2 norm of this state, and there's a way to do that. So there's an exact algorithm that exactly computes the squared 2 norm, and so it produces an exact computation of the Born probability. That's courtesy of Rabi-Smith-Smolin, 2016. And it does this in a runtime that's polynomial in the number of qubits and the number of magic states, but is quadratic in this stabilizer rank. Later in Rabi-Gossett, sorry, was there a question?
Yeah, I have a very stupid question. The compute the squared 2 norm refers to this thing you introduced in the first slide, right? This PQ, because I mean the state is 2 normalized.
Well, the state is 2 normalized here, but then we're gonna post-select. We're gonna project and discard these qubits, and then what we're going to be left with is now a projected state, so it's no longer normalized, and its 2 norm is the Born probability.
Okay, cool.
Mm-hmm. Another question. The paper you refer.
Sorry, I was going to ask a question, but I got a trumpet going on in the background. So psi, it's upper bounded by 2 to the m. Is that correct?
Sorry.
So the stabilizer rank, rank has an upper bound, right? And it's
of 2 to the m. Yes.
M. Yeah. Okay. Cool.
Okay. Another quick question. So the paper you're referring to is this, like the T count paper. When I was giving a talk on this kind of complexity work with Philippe and Jonas and others recently, the question came up whether the T count problem is actually NP hard, and that was unclear somehow. I mean, of course, the best known runtime is exponential in the input size, but do you know whether this problem is?
What's the T count problem?
Or basically just, I mean, like the meaningfully formulated decision problem that minimizes the number of T gates in a given circuit.
Oh.
Never mind.
I don't know. I mean, this is this is a good question to ask gate synthesis people.
Yeah.
I don't know. I mean, my guess is a difficult problem, but I don't know.
Okay, fair enough. Thanks. Wonderful.
Makes sense.
Just another follow up. When you talk about the stabilizer states, is that a generic sort of statement that it's any stabilizers any group you could come up with, or is it particularly?
Yeah, so I mean specifically, the kind of quantum info notion of stabilizer states. So quantum states, pure quantum states that are stabilized by a commuting set of Pauli operators, maximal commuting set of Pauli operators.
Okay, yeah, cool.
Another kind of just basic question. So this, you're trying to decompose the T state to stabilizer states, but how do you make sure that they're kind of like a complete set so that it can be decomposed?
Oh, so for a fact that the T states can be decomposed because the stabilizer states include the computational basis states, which are a basis for the whole Hilbert space.
Oh, okay.
So you always know that you at least have a decomposition in 2 to the number of qubits, but you can do better.
I see.
And you might be able to do better in general.
Okay, thank you.
Okay, so I guess the key point I wanted to make is there is this exact algorithm that runs quadratically in the stabilizer rank and polynomially in everything else. But there was this big important improvement in this paper that using something known as the fast norm estimation algorithm, they could compute this 2 norm in linear time rather than quadratic time. And so you could produce a relative error estimate. So that's these sharp p-hard kind of quality estimates of these Born rule probabilities in time that scales linearly in the stabilizer rank. Okay, so this stabilizer rank is the focus of the paper I'm going to get to soon, and we're going to talk about upper bounding the stabilizer rank and hence upper bounding the runtimes of algorithms of this form, since they depend on the stabilizer rank. That's going to be the focus. We're going to get to that in a moment, but I want to just for a second have a little bit of an excursion into additive error simulators, just to kind of give a more complete kind of background and show some of the connections. Okay, so if we move and start considering additive error Clifford plus magic simulators, then a more natural notion to think about is the approximate stabilizer rank. This thing is basically a robust version of the stabilizer rank. So rather than requiring an exact decomposition of the initial state into a linear combination, we require just that the decomposition is close in some norm. It's in fact delta close. Yeah, so it's the minimum number of terms in the linear combination of stabilizer states that results in something that's delta close to our target state. That's the approximate stabilizer rank. And so we can kind of play the same game. And now we don't need to approximate these initial states exactly, but we can epsilon accurately approximate these initial states, and then we'll end up with a Born rule probability estimate that's epsilon close. And the runtime will scale like linearly in the approximate stabilizer rank, which will be substantially smaller. And yeah, typically these epsilons are polynomial size. These deltas are like 1 on polysmall. And so an algorithm like this is given in Ravi-Gosset. But I just want to say that I think that this quantity known as the stabilizer extent is another quantity that's associated with these, is perhaps the more fundamental quantity. And so I want to introduce this and talk about it a little bit and talk about the connections between these. So the stabilizer extent minimizes the L1 norm of the coefficients in your decomposition. So given your target state, you write it as a linear combination of stabilizers, and there's lots of ways to do that. And what you do is you try to choose the way that minimizes the L1 norm of the coefficients in this decomposition. And the stabilizer extent is that minimum L1 norm. And so the connection between these is I guess you could look at the stabilizer rank as a minimization of the L0 norm, because the 0 norm is the number of terms, and the 1 norm is what the stabilizer extent is. So it's kind of it's a smoother, better behaved version of the stabilizer rank. Okay, so another reason to kind of talk about the stabilizer extent is that the approximate stabilizer rank can be upper bounded using the stabilizer extent. So this first upper bound that says the approximate stabilizer rank is less than the stabilizer extent times a quadratic in the inverse epsilon was given in this Bravi et al. Paper. And then later we improved this to a linear behavior in inverse epsilon and a linear behavior in the stabilizer extent in this paper here. And so we could really think of these simulators as being extent-driven simulators because the approximate stabilizer extent and the approximate stabilizer rank and the extent are linearly related to each other. But also the stabilizer extent is much better behaved than this approximate stabilizer rank. And so it's kind of easier to compute things associated with the stabilizer extent. So for example, we know that it behaves multiplicatively for 1, 2, and 3 qubits. And so we can use this to give a tight characterization of the extent of many copies of the magic state. So we know this is the extent of many copies of the magic state. Also, for those who might care, this quantity is closely related to a notion that we called negativity in this paper here. And so you might find that interesting for this reason.
This L1 measured negativity of the Wigner function.
Yes.
Okay. Mm-hmm.
And another reason you might think of this as more fundamental is because there are other examples of simulators where the extent arises more naturally without having to go through this approximate stabilizer rank notion in the first place. So here are 2 examples, and this result here gives a simulator that's kind of the current state of the art for simulating pure state quantum mechanics. So quantum mechanics in the pure state picture. And these results here give the current state of the art for mixed state simulators. So this might be of interest to you, Jens. And I want to say a little bit about the mixed state simulators because there's, it kind of tells you something about this picture and how it's actually a bit richer than one might expect. So in this paper here, we defined 3 monotones. So 3 different kind of notions of R, this resource, which we called the mixed state extent, the dyadic negativity, and the generalized robustness. And we show that they have this relationship. So smaller means faster simulators, because we constructed a simulator that that scales according to each of these resources. Interestingly, all of these are equal to each other and to the extent in the case that these are pure states. So the extent is only defined on pure states, but these things all equal exactly the extent for pure states. And so you can think of these as 3 different generalizations of the stabilizer extent into the mixed state picture. And so you see that, I guess, choosing a free subtheory and this notion of distance can actually be quite intricate and detailed and can change from slight variations even when we are restricting ourselves to Clifford plus T. And that's kind of all I want to say about this background and additive error. And I want to now move on to talking about the upper bounds on the stabilizer rank. Is there any questions before I move on?
I'm still a bit, so the stabilizer rank is like, I guess there's a fairly intuitive interpretation of it, but from what you've just said, is the extent now more of a, how to interpret it more? Like, I think I kind of missed it.
Yeah, I think, I mean, I argued that the extent is the more fundamental notion, but then didn't really say why and how to think of it in a conceptual way that makes it more fundamental. And I think, I really think that the most fundamental, like the way to think of it in a fundamental way is through this quasi-probabilistic picture in terms of negativity.
So it measures the quantumness or something.
Well, I guess when you construct simulators that are based on sampling, what you can do is you can to represent this state psi, what you can do is try to randomly sample a stabilizer state from some probability distribution such that the behavior of sampling this stabilizer state and then doing a bunch of operations with it mimics the behavior of this sample using this guy. And if you're going to do that, then you have to construct certain probability distributions and do certain tricks. But when you do these sampling procedures, you're going to find that the runtime of these tricks is going to scale in the one norm of these, because you have to normalize certain probability distributions. And it involves dividing by the one norms of these things. So, I mean, it's kind of pretty involved to explain it, but if you've seen these kind of simulators, it's kind of, I guess, conceptually, the notion of stabilizer extent makes sense, and one can see how it connects to negativity and runtimes of simulators.
Okay, all right.
Okay, so I want to kind of get to the topic of the talk, 35 minutes in, which is bounds on the exact stabilizer rank. So here's the definition of stabilizer rank we saw earlier, and I just want to kind of give an overview of what we know about the stabilizer rank, everything we know about the stabilizer rank. So first, upper bounds, and here we're going to look at m copies of a magic state, and assuming that these sharp p hard quantities take exponential time to compute, then this thing should be like 2 to something times the number of copies. And so what we're going to do is bound alpha, this exponent. And Brivey-Smith-Small in 2016 gave upper bound for alpha. That's around 0.468. This was later improved by Lucas Kochia in 2020 so there's a slight improvement in the third decimal point. And this paper that I'm presenting today will we get yet further improvement to, sorry, that date is wrong, it should be 2021, but to this quantity here. So this is this is going to be theorem 1, and I'm going to talk through this in a moment. But before I do, I want to talk about what is known about lower bounds, because on the lower bound side, we expect to find some exponential lower bounds, but the lower bounds are actually pretty far from exponential at the moment. So Brivey-Smith-Small showed a square root lower bound for the stabilizer rank. And recently, this was improved to a linear lower bound. This paper here showed a linear lower bound for qubits, and just recently, this paper here showed a linear lower bound for qubits. Okay, so we see that there's a very big gap between the upper bounds, and the upper bounds are exponential, and the lower bounds linear. And there's a clear problem there. So I want to just make a comment about the fact that all previous upper bounds of this type were quite different to the approach that we're going to outline. So I want to just talk about what the previous structure was for these upper bounds. This is a screenshot of the Brivey-Smith-Smolin paper, where they showed for, so here n is our m, it's the number of copies of the T state. So they show for each of these number of copies of the T state an upper bound for the stabilizer rank, and they comment that they believe this is tight, and in fact we'll show that it's actually not tight in this case, so we get an improvement here. But this is actually computed manually using kind of simulated annealing procedure. So it's like a heuristic search over some huge space to try to find linear decompositions of these states. And just to kind of give you an idea of how big a space we're searching over to get something like this. So you're trying to search for decompositions of 6 qubits. And there are approximately 300 million 6-qubit stabilizer states. And if you're looking for rank 7 decompositions, that's 300 million choose 7. So we're talking about these huge number of kind of spaces to choose from. So you're trying to search over this giant space, and of course it's going to be very hard to find these things. But if you do find a particular decomposition, then these quantities kind of upper bounds arise. So you will see that 6 and this 7 actually come from the 6 and 7 here. And how that works is kind of straightforward. So there's this property of stabilizer rank known as submultiplicativity, which says that if you take a tensor product of two states, then the stabilizer rank will be less than the product of the stabilizer ranks of each. And so looking at the fact that you have 6 copies for a rank of 7, you can kind of use that to construct, this is an asymptotic result. So asymptotically, for m copies, you could do that with 7 to the power of m on 6. And that's how you get alpha equals 0.468. So in general, these procedures kind of find a good decomposition, and then they use this blocking strategy to attach blocks. And our procedure is a little bit different. So let me just try to, before I kind of show our proof, I want to maybe just talk about some of the properties of the stabilizer rank. So we've already seen that it's submultiplicative. It's also subadditive in the sense that if you take a linear combination of two states, then the stabilizer rank will be less than the rank of each individual state. I'll add it up. And these are kind of clear to see if you just imagine writing each of these out as a linear combination of stabilizers. Also, they're Clifford and scale invariant, and that's also clear if you have a state and you apply a Clifford to it. Well, if you imagine the linear combination of stabilizers, the Clifford would be applied to each of the stabilizers, giving you another stabilizer. So that same decomposition here would suffice here, and hence you get a Clifford invariance. But also importantly, it's scale invariant. So it doesn't matter what numbers we multiply by. We don't care about any kind of normalization factors and everything. All that matters is kind of proportionality. So you'll see a lot of proportional 2 signs with no normalizations of states.
I see. That's also why in 2 that's not a typo, right? There's no A and B on the right hand side, but that's precisely your point. Right? Yeah. Okay. Good.
Yeah, I probably should have ordered these in the opposite order. Anyway, non-increasing under Pauli projections. And so if you take a state and you do a Pauli projection, so I plus Pauli, then this won't increase the stabilizer rank, In general, we get something that has a lower stabilizer rank, and the reason is because doing a parallel projection on each stabilizer gives you another stabilizer state. So stabilizers are closed on the parallel projections. Okay, so with these kind of properties, we can try to prove this theorem. We just need one more thing, which is to kind of define some additional states. So we've already seen the T state, and I want to define T perp, which is just the parallel Z acting on T. And so it just flips this phase from a plus to a minus. And I guess what's key is that they're orthogonal to each other. And now we can define this cat state, cat M, which is just a linear combination of the M-fold product of T's plus the M-fold product of T perps. Okay. And now the theorem kind of has these, the proof has these steps. So first we're going to prove that this alpha quantity is asymptotically the same for the M copies of the T state and for M copies of the cat or the M-fold cat state. This alpha quantity is the same asymptotically. Okay, so how are we going to do that? We're going to note this inequality, which basically says that the stabilizer rank of the T state is bigger than the rank of the cat state and less than 2 times the rank of the cat state. And if you believe this, then this statement is kind of clear because when you take the logs, this ends up being +1. And then when you divide by M, asymptotically as M goes to infinity, the difference between these two ends goes to 0. And so they're all the same. Okay, so now we just need to kind of show this equality. To show this part, we note that the cat M is proportional to taking the T state and then applying a stabilizer projector. Because recall the cat was like a bunch of T's plus a bunch of T perps. So the I term gives you the bunch of T's, and the tensor product of Z's gives you a bunch of T perps. And now we just need to use property 4, which says that if you project, the rank can only decrease. And so this part of the inequality is true. And to show this part of the inequality, we note that the T state could be constructed from the cat state by projecting just the first qubit onto T. Then it's clear that this projector onto T can just be written as a linear combination of two Cliffords, and so expanding into 2 terms using subadditivity and 0.3, we get this inequality. Okay, so that kind of shows this first part. That
so the cat state has a lower rank potentially than, it just seems counterintuitive. But I guess you're okay. All right, I can sort of, I see your argument, but it just, you make this massive superposition of this and lower the, okay.
Well, I mean, it's a superposition in the T basis rather than in the computational basis, and this is maybe the reason why.
Yeah, okay, I guess you can't necessarily say, yeah, okay, sure.
Yeah, and here is a nice one. The cat2 is actually the normal cat2 that we think of in the computational basis, like 0, 0 plus 1, 1. And so the cat2 is a stabilizer state. It has, I mean, it's one of the Bell states, right? It has rank 1. So the second step of this proof is that the cat6 has rank 3 and the cat2 has rank 1. And for this, we just did it by hand. I think Hammam spotted a decomposition of the cat6 by hand. And the reason you can do that, and the reason this approach works, because the rank is only 3. It's not 7, and so it's easier to see the lower rank stuff, and it's easier to kind of try to find the lower rank stuff for the cats because the cats tend to have lower rank than the T's themselves. And so
that's also obviously tied, right? I mean, you can probably, of course, that's found by making use of intuition, but I guess just by an exhaustive search, you can see that this is at a tight bound, so you cannot improve this number.
The tightness of the bound. So all we need is an upper bound. The tightness of it is not trivial, and David showed the tightness by showing that it's not rank 2. And the method he used was to show that basically rank 2. So we're looking at the expectation values with respect to all powers.
Yes.
And there's some structure that a rank 2 state must have, and
that's not the case in this.
Cat 6 does not have that structure.
Okay.
Yeah,
cool.
and that's what was used, but actually this kind of raises something that I'll talk about in the open problems, which is it's very difficult to actually show that your rank 3 decomposition is optimal. There is no rank 2 decomposition. So if you had a rank 2 decomposition, it's easy to show that you can't have a rank 1 because this thing is not a stabilizer. So non-stabilizerness is easy enough to show, but as soon as you get to rank 2 or 3, showing something that doesn't have rank 2 or 3 is hard. So even for those really small numbers. Okay, so the final ingredient is kind of this. It is quite new in what we're doing, which is that we can basically make big cat states from these little cat states. So we have this cat 6, and we have this cat 2, and we're going to glue them together. So we're going to take L copies of the cat 6 and L minus 1 copies of the cat 2, and we're going to be able to glue them together in a way to get a big cat that's like 4L plus 2 qubits. And the way this construction works, I have a diagram of it here. Basically, here are your cat 6s, and you do a cat 2 that kind of glues one of the 6 qubits here onto one of the 6 qubits here. And what do I mean by gluing? If we look at, say, an example where we have 2 copies of a cat M state, and we project onto a cat 2, where we're going to take, this cat 2 is going to act, one of the qubits is going to act on the first copy of the cat M, and the other qubit is going to act on the second copy of the cat M. And so this is what it looks like. This is the cat 2 here. And this is the first copy of the cat M and the second copy of the cat M up to normalizations. And so when you take this product, you're going to get mixed terms, right? You're going to get 4 terms. One has a string of T's and another string of T's. One has a string of T's and now a string of T perps. And then you're going to get the T perp and the T's and the T perp and the T perp, right? And this projection here is going to kill the mixed terms and only leave the string of T's plus the string of T perps. And that's kind of clear because when this hits 1 qubit from here and 1 qubit from here, it's not gonna allow mixed terms because T is orthogonal to T perp is orthogonal to T. And so by doing this kind of stringing, you can make these big cat states out of little ones. And then using submultiplicativity, you can show that the rank of these big cat states could be at most the product of the rank of these smaller cat states, right? But the cat 2 has rank 1, so it doesn't contribute anything, and the cat 3 only has rank 6, so we get this upper bound.
Mm-hmm. I see. And this trade-off has been optimized, right? I mean, on that level, there's nothing one can do about the bound anymore, right? In this kind of decomposition, I'm sure you have thought about this.
Yeah, well, I mean, it's been optimized to the extent that we could optimize it, right? I mean, there could be potentially nice configurations that one could think of, but the longer you make this cat, the better it gets. And so asymptotically, this is the scaling we find. You might find some, I don't know, nice tricks with different decompositions where maybe you want to do something different. And actually, we might see an example of this, time permitting. I do notice that we're kind of running out of time. How much time do we have, Jens?
Let's do it this way. Let's be relaxed about time. I mean, if somebody has to leave for some other meeting or something, I mean, please feel free. Take your time. I mean, don't. I'm quite intrigued of what you have to say now on the proof. Don't rush.
Okay, cool. Well, we're not too far from finished, because I'm gonna just kind of summarize the rest of the results without much proofs, and maybe very high level sketches. I'm going to say that, in addition to kind of showing this upper bound on the T states, we also showed a rank upper bound on the face states. So the T states are kind of, this is the stabilizer polytope. This is the T state here. It's between the plus and the I. And the face state is another magic state. Here's the kind of definition of it. And we also showed a upper bound on the stabilizer rank of many copies of the face state, and it happens to be exactly the same. So in addition, we showed an upper bound on the stabilizer rank of general equatorial states. So equatorial states are, I write them as R theta. So they're states of the form 0 plus some phase times 1. So they live on the equator of the block sphere. And we show that the stabilizer rank of an equatorial state is upper bounded by 2 to the half m. So now this exponent is a half rather than 0.396, but this is for a general class of states now. And the kind of idea is somewhat similar, but some important differences. So we're doing a similar thing of making a big cat from small cats. So we again define a notion of a cat state for these equatorial states. So given some R theta, you multiply it by Z, you get its perp, and then we can construct cat states in a similar way. And then we found the explicit decomposition of the cat 6 for an arbitrary R theta. Sorry, this is the and here is a picture of how we glued together these cat 6s to make a big cat for these equatorial states. So here you notice that instead of using the cat 2s, we have to use cat 6s to glue cat 6s together, because that was better than using the cat 2s. Because of the changes in for R theta, the cat 2s had a higher rank than 1, and that made it not worthwhile using the cat 2s. So again, we can kind of go from the cat of these equatorial states to the equatorial states themselves by projecting one qubit onto the equatorial state. And this can be decomposed into a linear combination of Pauli's, which gives us at most a factor of 4 difference between the rank of this and the rank of this, and that gets washed out in the asymptotics. And so we kind of end up with that upper bound there. And here is the explicit decomposition of the cat 6 into 4 stabilizer states. So here's one of the stabilizer states. Here is the other. Here is one where this E6 is, I believe, it's code with only even weights, and this K6 is E6 with a bunch of control X's on it. I guess the details aren't important. Maybe this is just to kind of convince you that there really is a decomposition. You can look at the details in the paper. Okay, and another theorem we show, which is kind of the full generalization, the full picture for single qubit states. So for an arbitrary single qubit state, we show a stabilizer rank upper bound that is basically 2 to the half, but with this prefactor of m+1. And the way this works is, firstly, you notice that these states are in the symmetric subspace, they're permutation invariant. And so we can construct a basis for the subspace that's made of entirely equatorial states. So we have to choose n+1 equatorial states that span the symmetric subspace, and we do that. And then by theorem 2, we know the stabilizer rank of each of those. And then by using sublinearity, so there's at most n+1 of those, which is where this n+1 comes from. And using sublinearity, you can kind of show this upper bound. Okay, so that's that. And finally, we show a upper bound for the, or rather, we show an upper bound for stabilizer rank of many copies of a T state in terms of the stabilizer rank of a code state. So this is kind of, I guess we're trying to show a connection between these more general objects. So we're kind of generalizing this idea of we had with the cat state to more general constructions of code states, where if you could get a good low stabilizer rank kind of decomposition of a code state, then you could hope to use that to upper bound the rank of the T state. That's kind of what this theorem is doing. So it tries to upper bound this alpha in the stabilizer rank by saying that if you construct some code state with a known stabilizer rank, chi of L, then alpha must be less than this quantity here. So let me try to unpack that just a little bit. So L is some linear code that lives in a, it's a binary linear code, lives in Z2 to the M. And it has dimension K, which has to be less than M on 2, otherwise this construction won't be helpful. And if you have such a code, then you can define these things called code states. So we'll write them like this. And so the normal linear code can just be written in terms of generators. So you have, it's K dimensional, so you have K generators. Each one of these is a bit string in Z2 to the M. And the set of them generates some code in Z2 to the M. Now we're going to construct the state from this code. And the way we're going to do that is we're going to use each of these generators to define a projector, a Pauli projector. So first, this Z with a GI in it is basically a string of Pauli Zs and Pauli Is, where of length M. So each time one of these generators, so this generator is a string of zeros and ones, and whenever it's a zero, we get a tensor I factor, and whenever it's a 1, we get a tensor Z factor. And so we get a string of Pauli I's and Z's that correspond to this generator. And so that defines the Pauli string, Z of GI. Given that Pauli string, we can define a Pauli projector, P of GI. And then we can think of this code state here as simply starting the T state and then multiply that T state by all of these projectors. And I mean, we know that like these are a commuting set of Paulis, and so they're isomorphic to like addition in binary strings, and so you basically get a code. It's a linear combination of all code words that are strings of T's and T perps, which correspond to codes generated, or code words in L. Okay, so this defines some state, and a nice example of this is the cat state that we looked at earlier. The cat state has dimension 1. So there's only one projector, and that projector is I plus all Zs. So the generator is just the all one string. It's only got one generator. Okay. So this defines a code, and if for any such code, if we had a reasonable, if we knew its stabilizer rank or a reasonable upper bound on its stabilizer rank, then we could use that to upper bound the stabilizer rank of the T state. But I'm not going to go into the details of how to prove that. But I guess that's our final result. So with that, I want to maybe talk about some open questions. So first of all, I think lower bounds are very very far from what we might expect the true scalings to be, and so there's there's kind of a deep kind of open questions there. But it also, as I kind of briefly discussed earlier, even finding lower bounds for a fixed stabilizer rank and a fixed M is hard. So even just showing that a particular state cannot be rank 3 is a difficult task. And so developing techniques for that are kind of I think kind of it's plausible that we can make reasonable techniques there, and that might give us some conceptual insight into what's actually going on. I guess further typing of the upper bound is kind of obvious. Some examples of low rank codes would be really useful, and it would immediately imply tighter upper bounds for many copies of the T state. And also perhaps the development of better search algorithms for searching for the decompositions. I would also say that maybe a lot of the work that's gone into this topic, and it might be a feature of the topic itself, a lot of the work kind of shows some improvement in the scaling without really giving a good conceptual insight as to what's really going on, or why, or how to improve things further. So some conceptual understanding of the structure of T states as a linear combination of stabilizers would be really valuable and big progress. And finally, we have this algorithm that solves the sharply hard problems. So you could maybe try to apply it to doing things like computing weight enumerator polynomials or number set and so on. And we haven't really thought much about if there's any areas of application where we could actually get better results than existing algorithms. So I think applications are interesting. With that, I'd like to conclude, and thank you for your attention.
Yes, wonderful. Thanks for this wonderful talk and this stimulating talk. That was great. We had lots of questions along the way, but there will be more. I have surely lots of extra questions, but maybe somebody else wants to ask a first question.
I would have one short question. So Hakop, so first, thanks for the talk. And second, what do you think is the scaling of the stabilizer rank in the end, like the true one? Do you think it's exponential, or do you think something else is going on?
Oh, okay. I mean, I think it's exponential because the world's a very tricky place if it's not.
Yeah, that's right.
Yeah.
But yet the best lower bounds are what, linear?
Yeah, best lower bounds are linear.
And that's what I was thinking, right? I mean, also looking for lower bounds is probably like a very reasonable thing to do.
Yeah, and it's kind of, I mean, maybe just a comment, but like, having a really hard.
It's also much harder, right, to come up with new ideas for lower bounds.
Yeah.
It's a bit like in the fault tolerance questions, right, where you also have the question of upper and lower bounds, which are hugely different.
Yeah, and it's also, I mean, these lower bounds are, there's also an open problem in quadratic Fourier analysis that is connected to these lower bounds. So actually proving better than linear lower bounds in this setting would crack this open problem in the field of quadratic Fourier analysis as well. So it seems to be a difficult problem, not just a problem that maybe not enough attention has been paid to.
Mm-hmm.
I really don't know. I mean, one can see why it's difficult, because you have exponentially many, bases in the set of stabilizers to choose. And you're trying to kind of choose the best one for expressing this specific thing that doesn't play nicely with the structure of stabilizer states. But I think beyond that, there's very little conceptual insight that I have about this problem, unfortunately.
Cool. Yeah, thanks.
Maybe a follow up to this question to connect to the table you had in the beginning with the different sets of problems. Would like if there would be if someday some very clever guy proved the polynomial upper bound for this problem, would this collapse some complexity classes like sharp P into P or something?
Yeah. So if the stabilizer rank of many copies of the T state was polynomially upper bounded, maybe one possible escape would be that there are polynomial sized decompositions, but they're very hard to find, right? So there's only, you can write it as a linear combination of polynomial many stabilizer states, but finding what the stabilizer states is outside of classical. But in that case, I believe that we'll be in the setting where say BQP is only as hard as a BPP with some advice string of polynomial length, because that advice string would be basically telling you for each instance size what are the stabilizers in the decomposition. And then you can imagine scenarios even worse than that, where even the decomposition is in P. Like you could even find the decomposition itself classically, in which case I think that would suggest that some very hard problems are in P or in BPP.
Cool, thank you.
I have a question on the kind of proof technique itself somehow. I mean, you show this cute technique of like building big cats from small cats. You have this kind of 6 cats at the lower level, and then these kind of higher level cats. There's kind of 2 questions that I have here. One is like, can you iterate this? I mean, this is like a 1 in 6 structure. Can you maybe think of a tree-like structure and improve the bound by doing this over and over again? And the second question is like, why the cats? I mean, I understand why you have them in the proof, but I mean, it's just some proxy, right? I mean, another proxy could also work for which you can assess the stabilizer rank. It's just an intermediate quantity. So could you also optimize over other intermediate quantities than the cat or the cat 6 for that matter?
Yeah. So for the tree-like structure, I think we played around a lot with these and couldn't find anything. Is maybe the kind of cleanest answer I could give you. In terms of why the cat, and couldn't you go further? Again, I mean, we know that like if we had a low rank stabilizer decomposition of some other code state, not the cat, and maybe I should mention something here, which is that this construction here that I gave in this last theorem, if you plugged in the cat for the code, so the code that gives you the code state that gives you the cat state, then you will actually recover our optimal bound here. And so
Okay.
this is
I understand.
it's kind of and so you could say, well, why don't we just find other codes and that have low stabilizer rank and try them and maybe improve on this, and that's and we have tried that, but I think lots of people with lots of computational resources should try this if they're interested in improving this upper bound, because it's simply hard to find such codes.
Yeah, indeed.
Because you have to do the search,
right,
and there's a big space.
You also mentioned this in the paper, right? At the end, if I remember this correctly, that this you could also search over these linear codes. Okay, thanks.
Yeah.
Okay, understand.
Can I jump in here? I was just going to ask you about point 2. Maybe I didn't follow what that means exactly. It's so the upper bound's independent of theta.
Yes.
Yeah.
So for if you vary over all theta, you get the equator of the block sphere. You get all the states on the equator of the block sphere, and we're saying that any such state, if you take m copies of that state, then it has a stabilizer rank that's less than this.
So I see. So the alpha equals 0.5. So it's alpha equals 0.5 for theorem 2. But theorem 1 is smaller, right? So
yeah,
I see. So the T state lies somewhere in that theta, but it's
yes, but it's very special. Like it's got a special structure.
I see.
So in general,
Okay.
you could show that for an arbitrary m qubit state, the stabilizer rank must be 2 to the m. Because I mean, you could just do a simple counting argument to show that.
That's what I said initially, I think,
yeah.
Earlier on.
Yeah.
So my other sort of random thought is, why the 6-cat? Like, was that just because it's like almost the biggest one, you know exactly what the number is?
No, it's the best one that we could it's the best one for the upper bound. So I think we we found higher cats, but I think there's a jump from cat 6 to cat 7 that meant that it didn't give us tight upper bound.
I see. So if you could extend the table, you might get a tighter upper bound, maybe, if you could use a bigger cat.
It just becomes
somehow,
but as you get a bigger cat, you could use it to kind of construct. You get more T states, but it's at a cost of more stabilizer rank. And there's this competition, right? Which one increases? Like if they increase in the right ratio, then things work out well. But as the stabilizer rank gets larger, it's also harder to find such things. So you kind of have to give up at some point.
Yeah. Okay.
I have a question. So the stabilizer rank, do you expect A, your proof techniques, and B, similar results to translate through for the qubit case?
The lower bound translated through the qubit case. We haven't thought about the upper bound actually.
Okay, but would you expect like a similar technique where you write a qubit magic state in terms of these cats and then try to compute? And do you expect like similar generating functions to hold for the stabilizer rank of the qubit states like you have for the qubit case?
I honestly don't know. Like it would take me a few minutes to think about at least before I could give you a reasonable answer. So I mean, I think your guess is as good as mine right now.
There was a question by Alex, but maybe I put my question first because that's kind of to some extent following up on this, which is, well, you must be aware of all this discussion on boson sampling and Gaussian boson sampling and to what extent you can classically simulate that and so on. And there's been ideas on linear combinations of Gaussian states and so on. And clearly there's kind of a dictionary on everything from the discrete variable to the continuous variable setting where you replace stabilizer states by Gaussian states. You can think of linear combinations thereof and also of linear combinations of mixed quantum states. And there's an analog of the stabilizer rank and all that. So have you thought about the natural continuous variable simulation technique that really follows pretty much precisely along the same lines of thought? Have you thought about this? Is that interesting? Is that worth pursuing? What do you think?
I haven't thought about it. It does sound interesting.
what would the analogy to the T state, the magic state be for CV? Is it some
I don't know. I mean, again, well, I
TKT or
mean,
something?
also there's a bit of a, I mean, the T's, I mean, T magic states are a bit of a convention, right? In some way. I mean, there's good reasons to pick the T resources, but other non-stabilizer resources would also do the job. And it's a bit similar in the continuous variable world. You can think of number states or some other non-Gaussian state as a resource. That makes perfect sense. And there have been a couple of candidates thereof. And I wouldn't mind. I mean, well, maybe fix it to a number input state as a natural resource.
Perhaps another question. So coming back to Jens's first question, when you showed the quantum circuit, and he mentioned that when you represent it as a tensor network, depending upon the order of contraction, you could reduce the time overhead. So in your scheme, is there some analogous thing you could do to reduce the time by some sort of clever ordering or something?
What do you mean by in my scheme?
So when you're trying to compute the stabilizer rank, right? I mean, like the resource that you have is a magic state, right? But in the quantum circuit case, depending upon the order of contraction for the tensor networks, you basically reduce the cost of simulation. So is there some natural analogy in this case, or?
I guess, I mean, yeah, I mean, I don't know, because you know, there's the trouble in analogies. I could make an analogy. I don't know if it's a very good one. I guess maybe the analogy is that right now we have different kind of constructions for low rank decompositions, and you know, today this is the best we know, and that corresponds to some runtime for our simulator, and tomorrow we might have a better decomposition, and now we get a better runtime in our simulator, even though nothing fundamentally changed in our simulator. It was just that, you know, somehow upper bound wasn't tight, and we've improved it. And you know, a similar thing happens with these contractions, because they're, you know, it's hard to come up with optimal contraction. You know, you could kind of improve the contraction, and then suddenly your simulator improves. But it's because it wasn't tight. And it's, yeah, maybe that's an analogy.
Okay.
Alex had a question since a long time, so maybe we should have Alex now.
Yeah, thank you. So if I combine what I think I have heard in the talk, I hope my mind doesn't play games on me. Do I think right that 0.2 is essentially for free for all states if you go to the approximate case, because your like the L1 norm of your thingies are bounded by square root 2 to the m, so 2 to the m over 2. And if you have a polynomial accuracy, then this gives only a polynomial overhead of your chi. Is this right?
Sorry, what do you mean by polynomial accuracy?
So you had the delta. Like in the
do I need to change slides to go to like the slide that's relevant or something?
Yeah, I think it was quite in the beginning where you explained a bit about the approximate rank.
Okay.
There you had like
find that,
where you had shown that chi with respect to delta is psi times epsilon, times 1 over epsilon. So
so these here?
Yes, exactly. Yeah. So yeah, the epsilon is what I called the delta before. So if you have some polynomial accuracy, then this gives you just some polynomial overhead, if I get it right. And your overall scaling would then still be the exponential scaling, which will come from the exponential scaling of the psi. And the psi should in general be upper bounded by 2 to the m over 2.
These extents are actually quite well behaved. They're much better than 2 to the m on 2. They're more like 2 to the 0.228 m.
Even better.
Yep.
Okay, so like these. Okay, then this should mean that like 0.2 and some of the other points are in the approximate case sort of for free.
Yes, I understand. think you're right.
Cool, thank you.
Another question well, I'm not sure whether along similar lines, but I mean, you've thought about so much about the question in Wigner world, right? And to what extent, like the L1 norm of the negative chunk gives rise to overheads in notions of strong simulation and so on.
Mm-hmm.
So have you combined this kind of picture with Wigner world, which you could, but I mean, is there anything you can learn from this?
I mean, I think you know, in this paper that you saw me talk about at QIP, this one here. We kind of in a sense do this. I mean, in a sense, this was kind of my way of combining quasi-probabilistic world with stabilizer rank world, and that combination, I guess, requires a kind of generalization of the notions of negativity. So the notion of negativity, as it was presented in that original work, like the PRL 2015, was in the mixed state picture. So we were simulating density states, right? And in that setting, these decompositions you know, give you like real coefficients, and they can be positive or negative. And so the sum of the absolute values, which is equivalent to the L1 norm, is the measure of negativity. But in the pure state setting, you know, these coefficients can now become complex. And actually, in this paper here, we showed a kind of you know, first level generalization into where we have these complex coefficients, and we take L1 norms of them, and that's how we get this notion of dyadic negativity. But I think in this paper here, you know, we maybe take this analogy one step further, where rather than I haven't thought about how to explain this best. You know, I think about these things as, you know, rather than thinking about the contributions to the Born rule probabilities that occur at the end as a result of a sampling procedure at the start, you can just be perfect. So I mean, quantum circuits look like, you know, you start in some state, you evolve. So if you decompose this state into some linear combination of stuff, these linear combinations evolve in quantum land under like transformations, become vectors, and then these vectors turn into contributions of probabilities. Somehow they contribute to probabilities in the end. And in the past, you know, in the negativity papers, we thought about these, you know, all these decompositions and how they contributed to the final probability in the end. Whereas in this picture here, like I presented in this paper, we're just happy to do all the computation in quantum land, in vector land, and look at the amount of cancellation we get in the sums of vectors that are sampled from some space that has a distribution on it.
Yeah, I understand. Okay.
Yeah. So, I mean, I don't know if that's a, you know, that's not a very clear explanation, but
no, but I get the intuition. Thanks. Another thing I was curious to ask is I guess, and well, I'm quite sure you're aware of our paper that we jokingly called homeopathy, in the sense that, well, you know that random Cliffords are not for designs, but you can get the, approximate designs to arbitrary order if you add a number of resource states that's kind of constant, like sublinear in the system size, which is like crazy that you kind of uplift the non-Cliffordness to and you kind of amplify this by random Clifford circuits. And if you took a family of circuits of that type, what would your algorithm deliver? I mean, what would come out if you take one of these Clifford circuits plus a very small number of T gates, and then would kind of put this in contact with your simulation technique? What would be the outcome?
Which simulation technique? The one in this paper here, or
Yes, precisely.
or this one here?
Yes.
So we're simulating Clifford and a small number of T-gates.
Yeah.
Well, I guess here we present a simulator that scales like polynomial in the extent or linear in the extent.
Okay.
And so it would just simulate and it would give you the Born probabilities that you want to compute, but they would be to additive precision. Yeah, because this deals with additive error.
Yeah. Okay. Of course. No, of course that makes sense. Okay, that's very plausible, and of course the additive error matters a lot.
I mean, a kind of slightly more interesting version of that is what happens if you do this and you have quite a few T-gates. Like, these simulators can handle like 50 or 60 T-gates, but what if you had 100 or something that's quite a bit beyond? And there, if they're random, then and there's kind of a deep Clifford which you're trying to get if you want these high T designs, then we show that typically actually you can approximate these probabilities to exponential precision, like to exact machine precision.
I see.
Because typically somehow there's a cancellation and things simplify, which was kind of surprising and interesting. But...
Okay, wonderful. Yeah, super intriguing. Very nice. Thank you very much. That's great, and wonderful. Yeah, we had lots of questions. That's great. Thanks for all the
excellent
interest and so on. Are there?
Yeah, thank you very much for having me, and thank you everyone for.
Yeah, I did warn you that
long talk and
lots of questions. So is there any further question?
May I ask?
Yeah, sure.
Sorry,
I want to ask about. Oh, sorry. Go ahead.
Yeah,
sure. Just curious about the numerics. Is there any numerics to check the scaling?
Which scaling?
The bound that you mentioned. Is there any?
What numerics though? I mean, I'm not sure how you would check the scaling because we can have we can use our constructions to give an explicit construction of a decomposition. And then, I mean, you could certainly, try to plug this in to your computer and make sure that, the density matrix representation of many copies of, or the ket, the full vector representation of many copies of a T state equals this decomposition. We haven't actually explicitly done that check, but, they would probably disagree because of like precision floating point errors or something. But I don't know. I guess it's kind of, we trust the theory. I guess this is what I'd say. We haven't actually explicitly checked that the decompositions are correct. If I understand your question correctly.
I see. Okay. Oh, because I would imagine that it's super hard to compute this rank. Is it super hard to do numerical compute this rank and just check the scaling, or?
Right, it surely be exponential effort.
Yeah, I mean, I gave that example earlier where even just to compute the rank of 6 copies of a T state, where it was like.
Sorry, which page was that? Maybe I.
Yeah, it's a good question. I've now forgotten which page it was as well. Yeah, here.
Okay.
So you're talking about, the search space you're looking at. If you want to look at size 7 subsets of 8-qubit stabilizers, is something like 10 to the 48 size 7 subsets. So you'd have to look at 10 to the 48 combinations, and for each one, do some non-trivial computation in a product computation, and then see which one's the lowest. That's yeah. I mean, just out of the question, completely out of the question.
Okay.
I have a follow-up question about static space. Do you study the decomposition of magic state in whole stabilizer space, or is there any symmetry on magic state or other clue that reduce the dimension of stabilizer state space?
Yeah, that's a very good question. And you know, we've been thinking about this, and I've been hoping to kind of you know, try to come up with a kind of more conceptually driven, interesting kind of result that, you know, like makes use of kind of some of the symmetries. You know, like for example, you know, you can see that T state has some symmetries. I mean, it looks nice. It's permutation invariant and so on. But you know, I mean, to date we haven't been able to, and it's quite possible that this problem is, you know, not going to allow us to use those techniques because it has to be hard. I don't know. I haven't had much success, and I don't. Yeah, it's frustrating, but I haven't figured out the way to do that yet.
It's a good topic to be frustrated about, though.
Yeah, okay, thank you.
Interesting one. Wonderful. So, if there are no further questions, then let's thank Hakop again for this absolutely wonderful and stimulating talk, and also for this equally interesting discussion. I think it was great to hear it from the master and like go into all these details. That's absolutely wonderful. So thanks again for coming by. Let's follow up soon on other matters. And yeah, thanks again. That was really absolutely wonderful. And yeah, thanks for all, and thanks to you all for listening. That was great. Thanks.
Excellent. Thank you everyone for your attention.
Thank you.
Thank you, Jens.
Yeah, thanks. Great.